Okay, so right here in the introduction, they have a very important couple sentences. So in many cases, the eigenvalue, eigenvector information contained within a matrix A can be displayed in a useful factorization of the form A equals P, a matrix P, times a matrix D times the inverse of P, where D is a diagonal matrix. Okay, a diagonal matrix would be a matrix that only has, like along the diagonal you have values, but off of the diagonal you have zeros. Okay, right, and oddly enough, if we can write the matrix A as P times D times P inverse, if we can, we've learned different factorizations of a matrix. Like we learned, for instance, that a matrix A can be factored as L times U, a lower unit triangular matrix times a matrix in echelon form. And that's useful, but here's another useful factorization of a matrix. A equals P times D times P inverse. And they're telling us that this factorization enables us to compute A to the kth power quickly for large values of K. Okay, so, it's an interesting question, right? How does MATLAB or even your calculator compute A to a certain power quickly? MATLAB will do it much more quickly, right? Well, let's take a look. So in example 1, what they do is they introduce you to a 2x2 diagonal matrix given by 5, 0, and 0, 3. D squared would just be the matrix times itself, and that, interestingly, will just then be equal to another diagonal matrix, but the entries are 5 to the second power and 3s to the second power. Now, if we want to do D to the third power, that's just D times D squared. And if you, do the matrix multiplication, you're going to find that D cubed is the diagonal matrix whose diagonal entries are 5 to the third power and 3 to the third power. So in general, D to the kth power, we could quite easily say the diagonal entries are 5 to the kth power and 3 to the kth power, and the off diagonal entries are zeros. Okay, are there any questions on this? Who's comfortable so far? Okay, Eleanor's feeling good. Stefani's good. All right, so far so good. Okay, well, now they say, well, if we could write the matrix A, if we could express it as P times D times P inverse, for some invertible matrix P, P would have to be invertible because you have P inverse, and then a diagonal matrix D, then A to the kth power is easy to compute. Okay, well, let's see why. Let's go, hold on here. Let's see why. So in example 2, here they have this 2x2 matrix A, and they want you to find a formula for A to the kth power, given that A can be diagonalized, where P is this matrix and D is this matrix. Okay, so of course, the matrix P, it turns out the matrix P is going to be the matrix of whose columns are the eigenvectors of A. And the matrix D is going to be the diagonal matrix whose diagonal entries are the I want to say this right, hold on. The matrix P will be the matrix whose columns are the eigenvectors of A. And the matrix D will be the diagonal matrix whose diagonal entries are the eigenvalues of A. All right, so let's get a formula for A to the kth power. So P inverse, you can use the formula for finding an inverse for a 2 by 2. Okay, and let's go ahead and just kind of do this piece by piece. Okay, to derive a formula for A to the kth power. So A squared is just would equal P times D times P inverse times P times D times P inverse. But matrix multiplication is associative, which means I can write the matrix product this way, and P inverse times P is the identity. And this is going to give me P times D times D times P inverse. But that just equals P times D squared times P inverse. And you're going to get then what you have here on the right. Are there any questions so far? All right, well then let's go further along here. A cubed, all right, would just be A times A squared. Well, A is P times D times P inverse. And again, if you multiply judiciously using the associative property for matrix multiplication, that P inverse times P becomes the identity again. And now you're left with P times D squared times P inverse, which is P times D n cubed times P times D cubed times P inverse. Hence, you know, we're seeing a pattern here. In general, I mean, A squared was P times D squared times P inverse, and A cubed was P times D cubed times P inverse. So in general, intuitively, you should see that A to the kth power would just be the matrix P times D to the kth power times P inverse. And that then, of course, is equal to what we have on the right. But that's just the product of three matrices, and you could figure out all the components, right? I don't want to say components. Components are for vectors, but you could figure out all the entries. And now, oh my goodness, you have a formula for A to the kth power. You have a formula. Computers like formulas, right? Computers like formulas. So A to the 100th power, well, it would be a lot, right? But, you know, all you have to do is, you see every entry in that A to the kth power, which is the matrix A multiplied by itself k times, every entry of the four entries is a formula. How many think that's pretty cool? Yeah, Benjamin's liking it. Sure. So if a matrix A is diagonalizable, it's very nice. And of course, a matrix A is diagonalizable if the matrix A is similar to a diagonal matrix. Okay, that means A is equal to P times D times P inverse. for some invertible matrix P and some diagonal matrix D. Are there any questions so far? Okay, well, all right, so it's very nice if we can diagonalize a matrix A, and not all matrices, and these are square matrices, not all square matrices can be diagonalized. Okay, certain conditions have to be met, and that's what this theorem 5 talks about below. It's called the diagonalization theorem. Okay, I'll highlight it here. So a square matrix A is diagonalizable if and only if the matrix A has n linearly independent eigenvectors. And in fact, the D is the diagonal matrix. Well, A equals P times D times P inverse with D a diagonal matrix if and only if the columns of P are linearly independent eigenvectors of A. And then the diagonal entries of D are eigenvalues that correspond to eigenvectors in P. Okay. In other words, you have to have an eigenvector basis. In order for a matrix A to be diagonalizable, you need to have an eigenvector basis of your n-dimensional space. Okay, and the matrix A is n by n. So let's look at the proof of this. It's not hard to prove, actually. All right, what they do is they do this. Okay, they say, okay, let's say we're going to multiply matrix A times P, and the matrix P consists of, or the columns of the matrix P are the eigenvectors. The column vectors of the matrix P are the eigenvectors of the matrix A. Well, okay, if you remember about matrix multiplication, you could then write the matrix A times P as the matrix whose column vectors are A times V1, A times V2, and A times Vn. And you learned that before. How many recall that back when you learned about matrix multiplication? This kind of way to think about multiplying a matrix by matrix, what they're showing there. Okay, it's very familiar to Olivia, and all right, and Benjamin as well. Well, now let's also look at P times D, the matrix P times the matrix D. Now A is going to equal P times, well, I want to say this the right way. Well, no, let's just look at P times D for now. So P is the matrix of eigenvectors, and D is the diagonal matrix whose diagonal entries are the eigenvalues. And again, from your understanding of matrix multiplication, the matrix P times the matrix D would just equal the matrix whose columns are lambda 1 times V1, lambda 2 times V2, and so forth, up to lambda n times Vn. Okay, so far, are there any questions? Okay, well now let me, so we're looking at A times P, and we're looking at P times D. Let me go to the whiteboard for a minute. Well, actually, hold on. Let me go back to So let me go back to the ebook here. Hold on. Actually, I want to stick with the ebook. Is A times P equal to P times D? Should the matrix product, A times P, equal the matrix product, P times D? Let me kind of highlight here what I want to highlight. So I'm leaving a little bit of the highlight on there. A times P, P times D, should they be equal? Benjamin says yes. Why is that, Benjamin? I'll tell you what. Let's go to the whiteboard for a minute. Okay, eigenvectors of A. That's right, Benjamin. That's right. Let me go to the whiteboard for a minute. Okay, one moment. Let me try out my stylus here. I mean, let's just think about A times P. Let's just think about a 2x2 matrix. There's A times P. V1 and V2 are eigenvectors. P times D would be, again, this is based off of the proof of theorem 5. I'm just keeping it light. Okay, so is A times V1 equal to lambda 1 times V1? Similarly, is A times V2 equal to lambda 2 times V2? In other words, to show that A times P equals P times D, I'm trying to see if the column vectors in both matrices are equal. And that's what I'm asking here. What's lambda 1 and lambda 2? What do they stand for? Lambda 1 and lambda 2 in chapter 5. That's right, Nafani, eigenvalues. All right? Lambda 1 and lambda 2 are eigenvalues. What about vectors v1 and v2? What are those? You know, based on... Good, Nafani, those are eigenvectors. So if lambda 1 is an eigenvalue and v1 is the corresponding eigenvector, then will A times v1 equal lambda 1 times v1? Yes. And by the way, we're assuming v1 is a non-zero vector. But yes, that's the definition of an eigenvector. And similarly, A times v2 will equal lambda 2 times v2. Okay, again, this is only true. We're assuming lambda 1 and lambda 2 are eigenvalues, and vectors v1 and v2 are the corresponding eigenvectors. So this means then that A times P would have to equal P times D. Okay? But we can multiply both sides of this matrix equation. We can multiply on the right-hand side P inverse. Well, P times P inverse is the identity. So the matrix A would equal P times D times P inverse. Okay, which shows that A is diagonalizable. A is diagonalizable, but it's only diagonalizable if the matrix P consists of columns that are eigenvectors of A, and the matrix D consists of, it's a diagonal matrix whose diagonal entries are eigenvalues of A. And it has to be in the proper order, too, you know. Are there any questions on this? Okay, well then let me go ahead and get back to the book then. So this is what they're getting at then. Their proof is more general, but if we then go down again, see they equated the columns, you know, and basically, well, and then they say A times P equals P times D implies A equals P times D times P inverse. So they just did the proof a little more abstractly, but you know, we justified why it works, and so you have hence the diagonalization theorem. You see, if you want to diagonalize a matrix, you have to be able to construct the matrix P and construct the matrix D. You got to be able to find them. Okay, and that's now we know how to find them. The matrix P is a matrix whose columns are the eigenvectors of A, and the matrix D is the diagonal matrix whose diagonal entries are eigenvalues of A. And also, you need to have, if you have an n by n matrix, you have to have n linearly independent eigenvectors, or the matrix is not diagonalizable. Okay, so if there are no questions on that, let's look at an example here from section 5.3. I'm going to actually work through example 3 with you. Okay, so okay, if possible, diagonalize the matrix. That's what we're going to do, and we're going to work this example out by hand. Of course, for the exam, unless I tell you otherwise, I want you to work examples out by, answer questions by hand, right? Show the row operations and so forth. You can always use MATLAB to check, right? But I want to see the work because I need to see that you understand the concepts. So, okay, let me give you a moment to copy this down, this example. Okay, so what's the first thing that we have to do here? If we want to diagonalize, I don't know why it's doing that. If we want to diagonalize this matrix A, where do we need to start? So this is sort of like, you ever hear that expression, what comes first, the chicken or the egg? I don't know if you've ever heard that. It's kind of a riddle, what had to come first for a chicken species to grow, the chicken or the egg, My question to you is, what comes first, eigenvalues or eigenvectors? Good, that's right, Benjamin. You got to get the eigenvalues first. So how would you get the eigenvalues here? What special equation do you need to find the eigenvalues? Well, to get the eigenvalues, you have to take A minus lambda I minus lambda I take the determinant of that and set it equal to 0. That's how you find the eigenvalues, is by solving this equation. What's that special equation called? Do you recall from your notes last week? Okay, Hung, you're almost character, you're on the right track. Characteristic equation. Characteristic equation. Okay. So I don't know if Wheel of Fortune, they would have counted that answer right that you chatted out, but I'll count it. That's fine. You have the right idea. Okay, but we already actually found the characteristic equation for this matrix. If you remember last, how many recall, look back in your notes for section 5.2. Did we, do you recall that we found the characteristic, we found the characteristic equation? I think we did in section 5.2. If you could just check your notes on that and let me know. Pretty sure we did. It would be like the last thing we did last Wednesday from section 5.2. We've okay, maybe if one of you could let me know if you could confirm that. I mean, I'm like 100% sure I'm right on this, that we found the characteristic equation for this matrix A, but I just kind of want you to go back in your notes and look. Okay, Haley has it. Thank you, Haley. Okay, well, just so I'm kind of, having the problem all together here, what I did was I mean, the characteristic polynomial is equal, thank you, Haley, by the way. The characteristic polynomial is equal to 1 minus lambda over 1 minus lambda times lambda plus 2, that quantity squared. And of course, you have to use cofactor expansion to work it out. And what I did was I expanded along the first row here, cofactor expansion. It's difficult to use properties of determinants because you have that variable lambda in there. involved. Let me see one thing here. Actually, what I'm doing here, hold on. I'm not expanding along the first row this time. I'm expanding, let me see here. Well, I know what I know, but what column am I, what row or, well, what column am I expanding along here for this cofactor expansion that you see here? I mean, I know what it is, but can you tell me which column? First, second, or third? That's right. I'm expanding down the first column. And of course, it doesn't matter in cofactor expansion which column or row you use. In the end, you have to get the same answer. And so we get that 1 minus lambda times lambda plus 2 squared as the characteristic polynomial. Now in the 5.3 homework, what they do for a lot of the problems is they know you can find the eigenvalues. So they actually give you eigenvalues and then you go and find the eigenvectors. But I just wanted to do a problem, completely worked out. What are the eigenvalues going to be? Based on my characteristic polynomial. Do that a little better. Well, I'm going to set this equal to 0, right? Okay. So, and I want to say that, okay, how did I get down to here? You just got to manipulate all this here, manipulate it, and like I did previously in your notes for last Wednesday, you just manipulate the characteristic equation, get it factored. What are the eigenvalues going to be? That's right, Benjamin. 1 and -2. That's right, Hung. And so let me go to the next page if we're good. Okay, here are your eigenvalues. Lambda 1 equals 1 with multiplicity 1, because this factors to the first power here. And then lambda 2 equals -2 with multiplicity 2. Now that we've found our eigenvalues, we have to find 3 linearly independent eigenvectors of A. Okay, well, the eigenvectors come from solving, hold on. Where's my pen at? Hold on. One moment, class. Where is it? Ah, here it is. The eigenvectors come from solving A times X equals lambda times X. Okay, but that can be expressed as A times X equals lambda times I times X. And so A times X minus lambda I times X equals the zero vector. This is an aside here. And so that means A minus lambda I A minus lambda I times the vector X is equal to the zero vector. I is the identity, of course. And so this equation here is how you find the eigenvectors, and that's what I'm doing here. That vector equation corresponds to this system, this homogeneous system of equations. And if you take the matrix A and subtract the identity, okay, if you do that, you're going to get, well, you know, along the diagonal, 1 minus 1 is 0. Negative 5 minus 1 is negative 6. And 1 minus 1 is 0. And then the rest of the values stay the same. Are there any questions so far? All right. Okay, well, then let's continue here. Let me see here. So here, let's put my instructions in here. Here, I took row 1, and I swapped it with row 3. Here, I took 1/3 times row 1 and replace row 1 with that result. And then here, I took 3 times row 1, added it to row 2, put the result in row 2. May I move to the next page? Is anybody still copying? Or should I, maybe I should ask, so far, who's comfortable? Okay, Abby's comfortable. Thank you, Abby. All right, well, if we're good, then I'll move to the next page. So the second row, I'm going to get ones there. Okay, so now what I did was I took, hold on. Yeah, I took negative 1/3 row 2 and replace row 2 with that result. And then finally, I took negative 3 times row 2, added it to row 3, and put the result in row 3. Feeling more comfortable with this stylus. I'm starting to feel comfortable. Okay. So, okay, x3 is free. x2 equals negative x3 based on the second equation. And then x1 based on the first equation, x1 is equal to negative x2, but x2 is negative x3, so you get x3. See, what I could have done is just, I could have, well, yeah. I didn't get this quite in full reduced echelon form because of this 1 here, but it's fine. So the vector x, okay, which is the eigenvector, right? This vector x is eigenvector. I write that in parametric vector form. x1 equals x3, x2 is negative x3, and x3 is x3, and then I factor out the scalar. And so the basis for my eigenspace corresponding to lambda 1 equals 1 is just going to be this v1 vector here. 1, negative 1, 1. And I note that the dimension of my eigenspace is 1 because there's just one vector in the basis, in the basis for the eigenspace. We sometimes call that an eigenbasis. Eigen in Germany means self. Okay, I don't know if any of you knew that, but so we're trying to find this matrix P, and we're trying to find the matrix D. What should the dimensions be for matrix P? You know, if we're 3 by 3. Good, Haley. And so far, I have V1. What do I need to find now? To construct the matrix P, I found one eigenvector. What else do I need to find? I found one eigenvector corresponding to the eigenvalue of 1. What vectors are going to be in these two spaces here? Okay, Nafani, the other two eigenvectors corresponding to the eigenvalue of -2. Okay, so let's go forward then. If there are no questions, we'll move forward. All right, so with lambda 2 equals -2, that's the other eigenvalue. Again, we're going to solve an augmented system. Okay, and do the row operations. So again, now on the exam, I want to, we like our technology, but we don't want to forget the fundamentals. So, this kind of problem, I would expect to see some row operations, and that's what I'm doing them here as well. So row 1 times a third. Replace row 1 with that result. And then here, just going to take 3 times row 1, add to row 2, put the result in row 2. And then I'm going to take -3 times row 1, add to row 2, row 3, sorry, and put the result in row 3. And so now, I mean, and let me ask you, does it seem like these are difficult to solve, these systems of equations for the eigenvectors? I mean, does this seem hard to you? No, it's not hard. Not hard at all. Okay, we got 2 free variables here. We have 1 equation, 3 variables. 2 are free. X1 equals -x2 minus x3. I go ahead and write my eigenvector in parametric vector form. Remember, x is an eigenvector. I want to be a little careful how I say that. It's or a linear combination of eigenvectors. So we get the vector x equals x2 times v1. v1 is -1, 1, 0, plus x3 times v2. v2 is -1, 0, 1. So we found 2 linearly independent, well, we now have a basis. We have a basis for our second eigenspace. The basis is the basis v1 and v2. All right, are there any questions so far? Now I'll tell you, if we had only gotten, we got 2. I'm sorry, I shouldn't call them v1 and v2. I should call them v2. I should call these eigenvectors v2 and v3. right? Because just because we used V1 for the previous eigenvectors, so V1 and V3. So there's a basis, V2 and V3. So it turns out that we have 3 linearly independent eigenvectors. That's good. Now, if it turns out that we had only gotten, for this part, like 1 eigenvector, then we could not diagonalize the matrix A, because we need, A is a 3 by 3 matrix, so we need 3 linearly independent eigenvectors. So we can diagonalize the matrix A. So we can write A as P times D times P inverse. All right, so here then is our basis for our eigenspace corresponding to lambda 2 equals -2. Now we construct our matrix P. And there are 3 eigenvectors. Okay, give you a moment to catch up here. Okay. And of course, we have to construct our diagonal matrix D. The diagonal entries consist of the eigenvalues according to the multiplicities. So lambda 1 was equal to 1, and that eigenvalue had multiplicity 1, so it only occurs once along the diagonal. And then lambda 2 occurs twice on the diagonal. And the order 2 has to match. We had the eigenvector course V1, which corresponds to lambda 1 equals 1. We had that come first. So that means along the diagonal, the 1 has to come first. The order matters. Now, what I'd like you to do let's say this is the exam, and you want to do a check. Can you check in MATLAB that A, the matrix, if you take P times D times P inverse, Can you check to see it equals matrix A? I'd like you to try that. Okay, I don't think I need to put it in the recording, but man, let me give you a few moments to just do a little check on that in MATLAB. So see for yourself if A equals P times D times P inverse. And let's see if we get a few people who confirm that. It's seeing's believing, right? Okay, so we're waiting our first confirmation. Who's checking it out in MATLAB? Who's checking it out? Who's confirming this? Okay, Benjamin says it works for him. Okay. And do we have a second confirmation? Okay, Eleanor, it worked for you? Good, good. How many think this is really pretty cool? Yeah, I agree. I agree. Thank you, Eleanor. Thank you, Benjamin. All right, let me go ahead. If there are no questions, are there any questions before I stop the recording? Okay, I'll stop the recording.